Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Modeling the Brain During the Industry 6.0 Era. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Velasquez, in 2021, published on SSRN, the paper Artificial Hypothalamus, Artificial Intelligence and Mathematical Programming Integration, in which the foundations of artificial brains, and more specifically of the hypothalamus, are laid. The article, and others later, carefully studies the relationships between the structures of the neocortex, with those formed when a mathematical problem is atomized, to use large-scale optimization methodologies, oriented to the partitioning and decomposition of systems, and they define the artificial brain in semi-detail. This is a disruptive vision of artificial intelligence, considering the power of computers, the evolution of mathematics, and the Internet of Things. This conference explains in a summarized way this evolution, based on the current state of AI. A complementary document is Artificial Brains, Augmented Artificial Intelligence, Artificial Neocortex plus Artificial Hypothalamus plus Artificial Hippocampus. Digital Industrial Revolutions. Today, the evolution of industrial revolutions is conceived as Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability. Beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies, and ethical and conscious governance. AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university. However, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. Artificial brains as a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. Artificial brains are an invention of high, due to their expertise in complex modeling. The image shows a close-up of the human brain showing the activation of neurons and neuronal extensions of the limbic system, mammillary pituitary gland, amygdala, thalamus, cingulate gyrus, corpus callosum, hypothalamus. This indicates that the human brain is composed of groups of neurons which in turn are composed of groups of lower-level neurons, or individual basic neurons, called by high the atoms of the system. The central idea of the artificial brain is to build an artificial intelligence that mimics the human brain, leaving aside the approach of trying to represent the entire brain using a single network of artificial neurons. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus, and hippocampus. The hypothalamus is part of the thalamus. The structure of an artificial brain is made up of the artificial hypothalamus, hippocampus, and cortex, all of which perform functions like human equivalents. Artificial brains emulate the structure of the brain and use it to build the mathematical models. Don Santiago Ramon y Cajal has guided generations of neuroscientists like a lighthouse. Today he resonates with a new and unexpected vibration. For more than a century, science has looked at the cranial brain as the sole seat of higher neural complexity, relegating the heart to the noble, but mechanical task of pumping the blood of life. Modern research, armed with tools that the master could scarcely dream of, but whose arrival he prophesied, now reveals that the heart does not only obey, it also feels, processes and decides. The heart has its own neurons and its own brain. The image shows sinoatrial plexus, neurons, heart plexus, heart tissue, and valve. The components of the human brain have at least two levels. On the first level, there are the main organs such as the neocortex, the hypothalamus, and the hippocampus, and on a second level, the neurons that make the main organs. The image shows, on the left, the motor neuron of the spinal cord, on the center, the neurons of the pyramidal cell of the hippocampus, and on the right, the neurons of the pyramidal cell of the cerebral cortex. The living industrial ecosystems is how large brain systems operate, such as the neocortex, the hypothalamus, and the hippocampus, and the orchestration of swarms of cognitive robots. It is the way in which the thousands of neurons operate within these systems. Industry 6.0 and living industrial ecosystems. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems that function as living organisms. The first type of algorithm that solved the problem of economic dispatch was dynamic programming. Dynamic programming, DP, is a numerical technique for solving complex problems by breaking them down into simpler, overlapping subproblems, storing their solutions in tables, to avoid redundant calculations. The term programming in this context refers to mathematical optimization, not computer programming. The problems were faced as either deterministic or stochastic. Because it is numerical, there are many variations of the algorithms. Problems were solved based on a monolithic solution of the entire system. Taking advantage of the popularity of commercial algorithms, mathematical programming replaced numerical versions of dynamic programming. Problems were approached deterministically and solved based on a monolithic solution, implying a centralized approach. The realism limitations of deterministic mathematical programming was the starting point for incorporating large-scale optimization methodologies to solve stochastic programming problems. In these methodologies, Bender's theory and Lagrangian relaxation stand out. Conceptually, the two methodologies are similar. In general terms, problems are divided into two levels, the upper one related to the coordinating problem, and the second level with its slave problems associated with combinations of dimensions of decomposition. In the example, the subproblems are associated with the smart grids that must be coordinated. These methodologies are a solution method that allows parallelizing the problem and accelerates its solution time. However, the problem is solved monolithically, that means centralized. Smart grids, the Internet of Energy, and Industry 6.0 have brought about a fundamental shift in the mathematical approach to solving problems, giving rise to consensus algorithms to address the solution, as they do not require centralized solutions or human intervention. Consensus algorithms are essential protocols in distributed systems, like blockchain networks and smart grids, which allow multiple independent nodes to agree on a single state or value of truth. Its primary function is to ensure that the system operates consistently and securely, even if some components fail or act maliciously. In the case of smart grid optimization, the current solution is that each one acts autonomous and independent as a living industrial ecosystem, and together they solve the problems of economic dispatch or unit commitment. The rules of consensus are based on mathematical laws, such as the theory of duality. The consequence of this is to solve mathematical problems through artificial general intelligence. This vision, born of praxis, is becoming a new way of using mathematics. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The connection between all the subsystems, within and between them, is made by bioneurons. For this, biological neural networks are formed, through which information flows in the brain, and in general in the human body. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. This decentralized and autonomous way of acting is how the human brain operates, and therefore must be imitated by any artificial brain. Each of these superorgans is made up of neuron networks, and lower-level superorgans. For example, the hippocampus has at least two functions and two areas, one that stores memory data and one that manages learning. This chain of organs and neural networks forms our brain. Artificial brains come from neuroscientific studies. The construction of the artificial cortex determines the connectivity of the artificial neurons, which are associated with the atoms of the system. In mathematical models, it is common to use a matrix that establishes the relationship between columns with variables and equations with rows. These matrices are scattered. This is the basis of cortical modeling. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained, whose central organism simulates the board of directors. When all the models that make up a company are solved using the living organism concepts of Industry 6.0, the updated version of an artificial hypothalamus is obtained, and the board of directors is not necessary. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that controls the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. The algorithm that simulates the hypothalamus is assembled by Optex, the high's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Human brains, a swarm of neurons. Industry 6.0, a swarm of algorithms of artificial intelligence. In 1962, the Dutch mathematician Jacques Benders published his theory of partitioning, which is a transcendental, not the first, step in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The author believes that Benders never perceived that the true importance of his research lay in the fact that he had established the way in which two algorithms would communicate with each other, and they could become a universal language for communicating a swarm of algorithms. If large-scale multi-level optimization methodologies, based on the partitioning and decomposition of systems, are applied to obtain the smallest atom of a dynamic stochastic model, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms, working autonomously and permanently, to achieve the goal proposed by the decision maker. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. Joseph Louis Lagrange was an Italian mathematician and astronomer, whose main idea is Lagrange multipliers, a strategy to find the local maxima and minima of a function subject to equality constraints, using the implicit function theorem, Lagrange's seminal idea is to convert a constrained problem into such a form that the theory of an unconstrained problem can still be applied. The principles of Lagrange theorists are still the support of optimization, but solving real problems using their techniques is no longer valid. Without knowing it, Lagrange generated the foundations of communication between cognitive robots, which speak mathematics as their natural language, allowing them to move like an artificial hypothalamus. Today, the term human learning refers to the biological and psychological process by which human beings naturally acquire knowledge, and direct learning via the neuroplasticity of the brain using technologies originating in Industry 4.0. Machine learning is a branch of artificial intelligence that allows computers to learn and improve their performance autonomously from data, without being programmed with explicit instructions for each task, uses algorithms to identify patterns, detect mathematical relationships, and generate accurate predictions about new information. Algorithm learning is the learning carried out by an algorithm, which participates in a machine learning process, so that the next time it can use information from the past, and if possible, improve performance. Neuroplasticity is the brain's ability to change its structure and functioning in response to new experiences, learning, and stimuli from the environment. Basically, learning is physically rewiring our brain. When you learn something new, neurons communicate with each other using electrical and chemical signals, or brain algorithms. If this activity is repeated frequently, the connections, synapses, are strengthened. If they are not used, weakened, or removed, synaptic pruning. This plasticity allows networking. Learning creates new neural pathways. For example, when learning a language, your brain maps new sounds and meanings. Constant adaptation. It is not something exclusive to childhood. Although it is maximum in the early years, the brain can change and learn throughout life. Compensation. If one area of the brain is damaged, as in a stroke, plasticity allows other areas to reorganize to take over lost functions. Direct learning driven by technology. Ray Kurzweil is a 78-year-old American inventor, writer, and futurist, widely known for his predictions on artificial intelligence and biotechnology. Currently, he serves as Director of Engineering at Google, where he leads natural language processing projects. Kurzweil predicts that humans will develop emotions and characteristics of greater complexity due to the connection of their brains with computers, and that by 2045, non-biological intelligence will be a billion times more potent than all current human intelligence, marking an irreversible singularity in civilization. On a commercial level, these services have been available for several years, for example, skull tomography, used to detect bleeding, tumors, fractures or brain injuries after an accident. Magnetic resonance imaging, ideal for accurate diagnosis of frequent headaches, providing pain-free high-resolution images. Brain ultrasound, generally focused on soft tissues and specific cases. What is new will be the public use of these technologies for the learning process of the human brain. Direct learning powered by nanotechnology. In the 2030s, human brains will connect to the cloud, allowing us to send emails and photos directly to the brain, and back up our thoughts and memories. This will be possible thanks to nanobots, small robots with DNA strands that swim in the capillaries of our brains. It will be just as the use of learning tools has been for human beings. The concept of learning through nanobots is at the intersection of advanced nanotechnology and neuroscience, posing a future in which knowledge will be transferred directly to the brain, or where our cognitive abilities will be artificially enhanced. There is currently research that lays the groundwork for this type of interface. Some examples are thought control. Prototypes of DNA nanobots controlled by human brain activity have been developed. In proofs of concept, a human operator has activated nanobots inside a living organism simply through cognitive effort. Neural nanorobots. MIT researchers are working on devices such as the Cell Rover, nanometer-scale antennas that can enter cells and transmit signals without damaging them, allowing precise electrical stimulation of individual neurons. Biological sensors, nano-devices capable of monitoring biomarkers in real time, which will evolve into systems that detect cognitive fatigue or optimal learning states to intervene biologically. Scientific and computational models of brain plasticity generally fall into three categories: biological mechanisms, mathematical rules for learning, and functional reorganization frameworks. These models explain how the structure and function of the brain change in response to experience, development, or injury. Biological and structural models focus on the physical changes that occur at the cellular level. Synaptic plasticity, the most common model, focused on changes in the strength of connections, synapses, between neurons. Structural plasticity models changes in actual physical anatomy, such as dendritic arborization, branch growth, spine density, and axonal bud. Neurogenesis, the model of how the brain generates new neurons, especially in the hippocampus, even in adulthood. Metaplasticity, also known as plasticity of plasticity, this model describes how prior synaptic activity regulates the future ability of those synapses to change. Mathematical and computational models are used in neuroscience and artificial intelligence. These models simulate how learning happens through data. Hebbian theory, often summarized as neurons firing together, connecting with each other. This is the fundamental rule for activity-dependent plasticity. Peak timer-dependent plasticity, STDP, a more accurate model where the exact timing of signals determines whether a connection is strengthened or weakened. Homeostatic plasticity, a stay-the-same-through-change model, which describes how neurons regulate their own excitability to keep network activity within a stable range. Hierarchical Bayesian frameworks, these use statistical machine learning to model how the brain integrates various sensory and behavioral data to update its internal maps. Functional reorganization models describe how the brain reassigns tasks to different regions, often following injury or sensory loss. Homologous area adaptation, when the function of a damaged region is taken over by the corresponding area in the opposite hemisphere. Intermodal reassignment occurs when a brain region normally used for one sense, such as vision, is recruited for another, like touch in blind people. Map expansion, the enlargement of a cortical representation, like the map of a finger in the motor cortex, by repeated practice of a skill. Donald Oldingheb is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior in 1949. Hebb has been described as the father of neuropsychology and neural networks. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. Hebb's theory has shown that learning does not increase the number of neurons, but it does increase the connectivity between them. Donald Oldingheb, July 22, 1904, August 20, 1985, was a Canadian psychologist who was influential in neuropsychology, where he sought to understand how the function of neurons contributed to psychological processes such as learning. He is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior, 1949. Hebb has been described as the father of neuropsychology and neural networks. His views on learning described behavior and thought in terms of brain function, explaining cognitive processes in terms of connections between neuron assemblies. Hebb concludes that the persistence, or repetition of a repetitive activity, or signal, tends to induce long-lasting cellular changes, which promote its stability. When an axon of a neuron A is close enough to excite a neuron B and repeatedly participates in its activation, processes of growth, or metabolic change, occur in one or both neurons, so that the efficiency of A to excite B increases. How do human brains learn? According to Hebb's theory, 1950, we learn if we form new synaptic connections between neurons. Learning is a new relationship that is created between neurons, and remembering is to keep that relationship socially active. When we are learning something new, neurons from different brain regions communicate with each other. With more exposure and practice over time, your brain creates stronger, more efficient communication between neurons. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. This principle suggests that the concurrence of neural activity is the basis for learning and memory. Synaptic strengthening: when a presynaptic neuron and a postsynaptic neuron are activated simultaneously, the connections between them are strengthened. Activity-dependent plasticity: the efficiency of synaptic connections is not static but can be modified as a function of neuronal activity. This plasticity is essential for adaptive learning and memory. According to Hai, the most important question Hebb solves is learning due to the addition of new cells in the brain? Learning is not about new cells, it is about new connections. Because of the creation of new and more efficient connections in the brain. Hebb's theory is based on the plasticity of the brain. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus: storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. From the point of view of Hai, one part of the artificial hippocampus processes the information stored in the other part, to develop a learning process. Learning takes the form of the generation of new neural connections, which must be stored in the artificial cerebral cortex, to be used in the future by the artificial hypothalamus. This high vision of artificial intelligence, built from the workings of the human brain, is currently unique in the world. Brain engineering. The future of Industry 6.0 is now. Brain engineering, commonly referred to as neural engineering or neuroengineering, is a multidisciplinary field that combines engineering principles with neuroscience to understand, repair, replace, or improve the nervous system. It sits at the intersection of biology, medicine, and technology, focusing on creating devices and models that interact directly with living neural tissue. However, this rapid advancement has triggered significant neuroethical debates regarding privacy, identity, and the boundaries of human autonomy. The key pillars of brain engineering are brain-computer interfaces, BCIs, systems that allow direct communication between the brain and external devices, are used to help paralyzed people control prosthetics or computers using only their thoughts. Neuroprosthetics, artificial devices designed to replace or enhance damaged neural functions. The most successful example is the cochlear implant for hearing loss. Visual prostheses for the blind are currently being developed. Neuromodulation, techniques such as deep brain stimulation, DBS, and transcranial magnetic stimulation, TMS, that use electrical or magnetic pulses to modulate neural activity. These are used to treat disorders such as Parkinson's disease, chronic pain, and treatment-resistant depression. Neural imaging and signal processing, development of advanced tools such as fMRI, functional magnetic resonance imaging, and EEG, electroencephalography, two most common non-invasive techniques, and microelectrode arrays to record and interpret complex brain signals, help researchers decipher the language of neurons to drive robotic systems or diagnose disease. Neural tissue engineering, research focused on the regeneration or repair of damaged nerves using biomaterials, scaffolds, and stem cells, especially for traumatic spinal cord and brain injuries. Beyond clinical treatment, brain engineering is moving toward human augmentation, exploring ways to enhance memory, speed up learning, or expand cognitive capabilities. Deep sensory networks. The combination of Hebbian and predictive plasticity learns invariant object representations in deep sensory networks. It is the central theory of this section. Recognition of objects from sensory stimuli is essential for survival. To that end, sensory networks in the brain must form object representations invariant to stimulus changes, such as size, orientation, and context. Although Hebbian plasticity is known to shape sensory networks, it fails to create invariant object representations in computational models, raising the question of how the brain achieves such processing. This study shows that combining Hebbian plasticity with a predictive form of plasticity leads to invariant representations in deep neural network models. The local learning rule that generalizes peak neural networks, and that explains several experimental properties of synaptic plasticity, including metaplasticity and peak time-dependent plasticity. The model accurately captures the neuronal selection changes observed in the primate's inferotemporal cortex, in response to an altered visual experience. Thus, it provides a plausible normative theory that emphasizes the importance of plasticity predictive mechanisms for successful learning. Disentangling sensory stimuli with plastic neural networks. A. Schematic of an evoked response in sensory input neurons. Neural response patterns for different stimuli correspond to points in a high-dimensional space encompassed by levels of neural activity. The response patterns of different classes of stimuli, like cats and dogs, form a low-dimensional variety in space of all possible response patterns. Generally, varieties of different classes are entangled, meaning that the identity of the stimulus cannot be easily decoded from a linear combination of neural activities. B. Sketch of a DNN, left, that transforms inputs into untangled internal representations that are linearly separable, right. It should be noted that the sign of plasticity depends on whether the responses are above or below the threshold of plasticity theta. The learning rule enhances the synapses that are active when a cat is shown, while penalizing the stimuli generated by a dog. This effectively pushes the levels of neural activity apart from each other, preventing representation problems. C. Schematic of how predictive learning influences latent representations, left. Learning tries to pull together representations that frequently co-occur close in time, bottom. However, without opposing forces, such learning dynamics lead to representational collapse, whereby all inputs are mapped to the same output and thereby become indistinguishable, right. D. Self-supervised learning, SSL, avoids collapse by adding a repelling force that acts on temporally distant representations that are often semantically unrelated. E. Plot of postsynaptic neuronal activity over time and a Hebbian learning rule, which characterizes the sign and magnitude of synaptic weight change, as a function of postsynaptic activity. LPL, latent predictive learning. Oya's rule is a mathematical model for how neurons adjust their connection strengths over time. It is a modification of the standard Hebbian rule, named by the work of computer scientist Erkki Oja. A. Illustration of the process of generating synthetic data in 2D. Consecutive data remains predominantly within the same cluster, separated along the x direction, and is extracted independently using a normal distribution centered on that cluster, on the left. This data is fed into an artificial linear neuron that learns using latent predictive learning, LPL, on the right. B. Cluster selection of the features learned by LPL with and without the predictive term, PredOff, and by Oja's rule for different standard deviation values, sigma y. By varying sigma y, we obtain a family of sequences with different amplitudes of transitions within the cluster, above. LPL selects contiguous features and thus ensures that the neuron is always selectable for the group's identity. Oja's rule finds PC1, the direction of greatest variance, which changes to the direction of noise in sigma y equal to 1. LPL without the predictive component shows the same behavior. The selectivity values were averaged over the random seeds. The shaded area corresponds to a sigma y, under different versions of LPL. C. The mean neural output activity during training time for sigma y is equal to 1 under different versions of LPL. LPL initially increases its response and becomes saturated at a certain level of activity, even when the predictive term is turned off. However, without the Hebbian term, Heb. Off, the activity collapses to 0. LPL disentangles representations in deep neural networks. The classic Bienenstock-Cooper-Monroe, BCM, learning rule is used. A. DNN schema trained using LPL that uses two learning strategies, layered and end-to-end. By layers, the goal of each layer is to predict representations within the same layer, while end-to-end training considers only the representations of the output layer, and updates the hidden weights of the layer using backpropagation. B. Linear reading accuracy of object categories decoded from representations in the network output, after training 4 networks independently on natural image data with different learning rules, local layered, dark, and end-to-end, light. The bars are average. Pred-off corresponds to LPL but without the predictive term in the learning rule. Heb-off refers to the configuration without the Hebbian term type BCM, and Decker. Off is the same as the single neuron learning rule without the term decorrelationship. LPL yields feature high linear reading accuracy. On the other hand, when any LPL component is disabled, the linear reading accuracy falls below the pixel decoding accuracy, by approximately 32%, dashed line. C. Linear reading accuracy of internal representations at different layers of the DNN after layer training. The data points are averages of 4 networks, and the error bands, SEM, indicate that LPL representations improve up to 6 layers and then stabilize at a high level. On the other hand, the accuracy of the reading is close to the level of chance without the Hebbian component, and similarly remains at low levels when the decorrelating mechanism is switched off. When the predictive term is wrong, accuracy increases in the first few layers, but then decreases back below pixel level accuracy with increasing depth. The complete LPL learning rule applied to inputs in which the temporal contingency is destroyed, LPL shuffled, behaves qualitatively like a purely Hebbian rule. D. The dimensionality plus the error bands, SEM, indicate the internal representations for the different configurations of learning rules shown in B. When the Hebbian or the decorrelation terms are deactivated, the dimensionality of the representations collapses to 1. E. Average neural activity in different layers of the DNN after training with the different variants of learning rules shown in C. The exclusion of the Hebbian term, dotted line, leads to collapsed representations at all layers. LPL captures invariance learning in the primate IT. A. Schema of the simulation configuration modeled from the experiment of Lee and DiCarlo, 2008. Model inputs consist of images of objects presented in 3 different positions, x1, xc, and x2 on an empty canvas. After the original experiment, a targeted disturbance is performed on the simulated visual experience to which the model's network was exposed, left and center. Specifically, the identity of objects is changed during transitions from a peripheral position, for example x1, to the central position xc, while maintaining the other peripheral positions unchanged. B. Evolution of the object's selectivity as a function of the number of exchange exposures, top row, and observed in vivo, in the bottom row, data extracted and delayed from Lee and DiCarlo. Data are presented as mean values plus or minus the error bands, SEM. A distinction is made between pairs of objects exchanged, left, and non-exchange, center, positions, as well as control objects in the exchange position, right. LPL qualitatively reproduces the evolution of the specific remapping of exchange positions, as observed in IT. The control objects in the exchange position, the images not used during the training protocol, show no changes in accordance with the experiment. C. Average response to preferred objects, P, and non-preferred, N, depending on the number of exchange exposures. The change in the selectivity of P and N objects is due to the increase in responses to N, and the decrease in responses to P, both in the reference model, top, and in the experimental records, bottom. The data values are spike timing dependent plasticity, STDP, peaks. Latent predictive learning and spiking neural networks. A. SNN wiring diagram with 5 different input populations. B. Snapshot of peak activity for 5 seconds after LPL plasticity for inputs, top left, and lattice, bottom left, are separated into excitatory, black, and inhibitory, blue, neurons. The entry peaks are organized into 5 Poisson populations with firing rates that evolve according to 5 different temporal signals, top right. The population activity of 2 signals, P1 and P2, varies slowly and can be reconstructed linearly from network activity with high R-square values, while control signals are strongly limited, bottom right. C. Distribution of mean afferent synaptic strength per excitatory neuron group by input population. The slowly varying signal input connections are larger than those of random controls, left, but not when learning with the predictive term off, right. Error bars show minimum and maximum ranges. D. Signal selectivity is a relative difference between the signal and the control path for networks trained with different learning rules. LPL refers to learning with the maximum rule of LPL combined with inhibitory plasticity and inhibitory excitatory connections. Pred. Off corresponds to learning without the predictive term and Heb off to learning without the Hebbian term. Inhibitor off refers to an environment without inhibitory neurons, while fixed inhibitor indicates that the inhibitory weights remain fixed. The network with LPL and inhibitory plasticity acquires high selectivity to both signals. Selectivity is lost if the predictive term, the Hebbian term, or inhibitory plasticity is disabled. E. Average firing rate of excitatory neurons in the lattice for the different configurations in D. When the term Hebbian, Heb, is not adjusted, the maximum activity collapses to low levels in contrast to all other configurations where it is located at intermediate levels. F. Dimensionality of neural methods for the different configurations in D. Inhibition prevents dimensional collapse, even in cases where inhibition is not plastic. G. Average weight vectors of all excitatory neurons correspond to the input populations P1 and P2, left, and the distribution of relative neuronal selectivity, REL, among these populations, right. Most neurons become selective for either P1 or P2, but few for both signals simultaneously. The color indicates the relative preference of its weight vectors with respect to any of the signals, methods. H, same as G, but without an inhibitory population. Most neurons develop selectivity to P2 or mixed selectivity to both signals, and their weight vectors are more correlated. LPL accounts for spike timing dependent plasticity, STDP, and predicts metaplasticity of the STDP window. A. Relative weight change owing to LPL in response to a standard spike timing dependent plasticity, STDP, induction protocol, with varying spike timing, delta t, for 100 pairings at a repetition frequency equal to 10 Hz, NSET, and an initial value of variance, sigma square, equal to 0.1. B. Same as A, but with an initial value of sigma square equal to 1. C. Same as A, but with sigma square equal to 100. D. Relative change in weight as a function of repetition frequency for positive and negative relative peak times, plus or minus 10 ms. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.